So today I'd like to talk a little bit about the phylogenetic diversity measure. And in a very general sense, what we're doing here is, if we look at a set of species, say the species on an island or the species that we want to allocate extra money for conservation, we want to have some measure of the biodiversity of that set of species. And then we can compare and contrast between different sets of species and make decisions based on the score, the biodiversity score that we get. So I'll cover that in a bit more detail. And then I'm going to talk about finding sets of species which maximize this score. Because if this score represents biodiversity, then we'd like to know which sets of species contain the greatest biodiversity. And it turns out that usually there are a few different sets of species which all equally maximize the biodiversity possible in a particular phylogenetic tree. And so it becomes useful to look at how can we optimize another measure of something related to the species, some use in a different sense, while ensuring that maximal PD still holds. And what I'm going to cover today is joint work with Charles Semple and Mike Steele, and together we've got a paper called Counting and Optimizing Maximum Phylogenetic Diversity Sets, and that's available on arXiv now. So phylogenetic diversity, as we know it, or as we'll talk about today, is introduced in this paper in 1992 by Fay. And he aimed to bridge a gap that we saw, that a lot of what we're looking at before was looking at species richness, say on an island, to talk in terms of biodiversity. So that would simply be counting the number of species on an island. And more species is better, but not necessarily taking into account the relationships between these species. And so there's a gap between, the aim was to provide a working definition of biological diversity for conservation evaluation. We'll go and I've got the definition here, but firstly, I'm going to talk today inside a particular framework of phylogenetic trees. So I'll be looking at rooted phylogenetic trees and with weighted edge lengths. We'll have a leaf set of species X, and I'll always label these species X1 up to Xn. So we've got N species on the tree. And to begin with, we'll look at ultrametric trees. So those are ones where the tree represents time in some sense as we go down from the root. And so in this case, phylogenetic diversity becomes the sum total of the edge lengths in the minimal tree which connects our set S that we're interested in up to the root vertex. And so I'll just go through an example of that, and we can see the framework a bit clearer and what phylogenetic diversity means for that. So here's a phylogenetic tree that I've invented. It's not representing anything in particular. But at the top of the screen, labeled row, we have a root vertex, and time proceeds down the page, going through common ancestors of species until we get to the 11 species that we've got at the bottom of the screen there. And the length of each edge corresponds to the time difference between, between X7 and X8 and their common ancestor, which is 1 unit earlier in time. And I'll use vertical separation to indicate that. So vertices that are at the same horizontal position on a page in my diagrams will have occurred at the same time. Also. And so suppose we have this set of species I've circled at the bottom of the page, and we want to calculate the phylogenetic diversity of that set. Well, we connect these species all the way up to the root, and we don't add any extra edges anywhere. And then we go through and we sum up each edge once. And if you do that for this particular example, you find this set of leaves has a score, a phylogenetic diversity score of 22. And so we can compare different sets and contrast them and say, well, some of these will have a small score. So if you chose, say, 6, 7, 8, 9, and 10, they would have quite a small score on this tree compared to this set here we've got. But also we don't expect this set to be the maximum possible because we've got these two vertices, 7 and 8, which are quite close together in the tree. And nothing really happening on the right-hand side here with 9, 10, and 11. So it'd be nice to have a way to find a maximal set. And the good news is that we can do it and we can do it quickly. So quick greedy style algorithms can find sets that maximize PD for each size. And so in 2005, these two papers here, both independently provided proof that greedy algorithms do work to find what we'll call a size K MaxPD set if it contains K species. So a set with K species in it, which has the maximum possible PD score on our particular tree. And the way these greedy algorithms work is we choose a species that has the maximum individual score to start with. So the furthest distance from the tree. Now, in our framework, we're working with ultrametric trees. So we can choose any species to begin with. And then we look among the remaining species to find one of them that, if we were to add it into our set, would increase the PD score as much as possible. And we can do this iteratively again and again until we reach a set of K species. And that's great, that can be implemented quite quickly. And we always guarantee that we'll hit a set at the end, which does maximize the PD score. However, one problem with greedy algorithms, in a sense, is that we're always choosing one of the largest additional scores to add. Sorry, the largest marginal addition, in a sense. And there may be, at different points, many species which are equally helpful in raising the score as much as possible. And conversely, we might find that we choose species in different orders, but we end up at the end with a set of, say, 10 species, which has the exact same score, even though it has a different ordering. And so it becomes hard to tell how many sets have maximal PD on a given tree if we're just looking at the greedy algorithm. We can go through and look at all the possibilities each time. But even as I mentioned at the start, if we're in an ultrametric tree, then every species is the same distance from the root vertex to begin with. And so we can start our greedy set with any species. And so that gives an indication that there are lots of choices potentially going on. But I wanted to now to why we might find this a problem and how MaxPD sets are used in some recent research. And so why we would care about how many MaxPD sets there might be. And so there was a question right from the start of phylogenetic diversity being introduced of whether it's a measure on its own, or whether whether it's simply a proxy for other biodiversity measures or senses of biodiversity that we care about more, say functional diversity, which is perhaps the different attributes found in species, or feature diversity, or the way that humans interact with different species. And so these two papers are examples where people have tried to investigate then whether there is a direct link between maximal phylogenetic diversity sets and sets that are optimal in some other sense. And so, for instance, the first paper tries to compare a measure of functional diversity. So they looked at different attributes that mammals have, let's say, and on a random set, and compared those attributes to mammals out of a maximal PD set, and come up with different conclusions in both papers. Both of these studies recognize the fact that maximal PD sets are quite numerous in a lot of trees. And so when using MaxPD sets as a benchmark in this way, they made sure that they didn't select just one maximal PD set to compare against the random sets, but they chose numbers, I think 10 in both cases, 10 sets of, say, that represented 40% of the species in the tree, say, against a random set that contained 40% of the species in the tree. And then compared, say, how many plants were in each set that humans find useful and interesting in the second paper's case. And the question that arises is, well, if we don't know how many MaxPD sets there are on a tree, can we be sure that choosing 10 was a good choice? Are we sure that we've covered the set of MaxPD sets in an unbiased way as well? If we don't have a characterization of MaxPD sets, we might find, for instance, there are some implementations of the greedy algorithm that take a tree in Newick format and choose the MaxPD set that is furthest to the left. So whenever there's a equally greedy choice, this implementation chooses the one that appears further earliest in the list when the tree's in Newick format. And that might prioritize some species rather than others and be a biased measure of choosing it. And equally, we can also think when we're choosing the random sets as a comparison set, perhaps these MaxPD sets are so numerous that we're ending up choosing some of the MaxPD sets and among our random sets as well, to an extent that we're comparing two very similar sets of sets, so to speak. And what I'll talk about today is that we can now characterize MaxPD sets in a way that allows us to work out how many there are on any tree and how many there are with a particular and their distribution throughout the tree a bit clearer. And that can allow us to address these questions. So here's an example of a maximal phylogenetic diversity set for the same tree. And it's similar to the tree we saw before, except instead of these species 7 and 8 being included, which I suggested were too close, instead we're going to include species 11 right at the end there. And that's allowed us to spread throughout the tree a bit more. But of course, this is not the only maximal phylogenetic set on this tree. Firstly, we'll call this set size 5 MaxPD set. So I'm going to show you a few size 5 MaxPD sets, and this might be a bit strange, but try to, as I flick through them, try to see which parts of the spanning tree or the minimal tree don't change. So some things will change between each MaxPD set, but some things won't. And so here's another. And hopefully, if we flick back through, you'll see that these edges were in common to all the minimal trees that we looked at. And it turns out you can look through all of size 5 MaxPD sets on this tree, and these edges will appear in every one. And so the idea that we had was, since these edges are in common to all MaxPD sets, well, what will happen if we remove them? And if we remove them, we'll get what I call the tall components, in this case, for size 5 MaxPD sets. Essentially what's happened is we've got this dotted line here with the name D4, which is the distance closest to the root. If we cut the tree off there, we're left with 4 connected components in the forest that results. So we have X1, 2, and 3 in one component, X4 is on a component on its own, and then we've got a component with 4 leaves and 3 leaves towards the end here. And the idea here is that if we look through all the MaxPD sets of this tree, we start to notice that we have to get at least one vertex, one leaf appearing in each one of these 4 components. So we're trying to choose 5 species that maximize PD, the PD score. And we noticed that for all of those sets, there's never any MaxPD set that completely ignores one of these components. And in some sense, these tall components tell us how spread out the MaxPD set has to be in order to cover enough of the phylogenetic tree. And then we can also look down. So this dotted line is what I call a branching height, and we call 4 a branching value, because 4 is a value that we can split the tree. There's a height where it branches into 4 separate components. And so we can't, no matter which height we choose, we cannot choose a height which would split this tree into 5 or 6. But the next height that we could look at is this height here, D7, which splits the tree into 7 small components, or short components rather. And again, we made the observation that if we look at any of the MaxPD sets from earlier, there will never be 2 species appearing which share one of these short components. So the short components tell us when 2 species are too close to really give the maximal PD score on this tree. And so we'll look back at one of the examples that we saw from earlier. And if you scan across, we can check that in each of the tall components, you'll find at least 1 species. And there's no species which will be connected below the second bottom line. No pair of species which would be connected if we look at just edges below the second dotted line. And so these are nice observations, but we were able to show in our paper that they always hold. These conditions are not only necessary, but they are sufficient to describe sets which maximize a PD score. So working through this, if we, excuse me, trying to choose a set of K species. So in our examples, we've had K equals 5. We need to look at the branching values which are closest to on either side of 5. And in our example, that was 4 and 7. But of course, if we're choosing a set with 4 species in it, it is a branching value itself. so we don't need to look at the branching values either side. And in this case, our set A is a MaxPD set if and only if it contains at least one leaf from each tall component and at most one leaf from each short component, which is the scope. And the nice thing about this theorem is it turns a problem of structure and length and different pathways through a greedy algorithm into more of a combinatorial problem. So there are lots of problems similar to this that we can build upon in mathematics, such as how do we choose 10 indistinguishable balls from 5 buckets of 6 balls or something like that. There's a lot of people have gone through and come up with all sorts of variations on that sort of problem and worked out ways to enumerate how many ways there are to do this sort of thing. So as I suggested before, when our chosen K, when we're choosing K species out of our tree to max, and we want to find a max PD set of that size, well then luckily the tall components coincide with the short components. And what we can do then is we can look at the sizes of the components and multiply those sizes together, and that tells us the number of ways we can choose one from each component. And in the other sense, when K is not a branching value, like the value 5 on our tree that we were looking at, we find that a generating function calculates the number of size K max PD sets. And I won't go into the details of that, but I've got it right at the end in case anyone's very interested and wants to have a look at what this generating function looks like. But the important thing is that we can use this generating function that calculates a polynomial for our tree, and it can very quickly enumerate the max PD sets on our tree of size K. Well, and of all sizes in a sense, we can go through and get one polynomial that we can construct for the whole tree. And for this tree before that I showed you some size 5 max PD sets for, it turns out that there are 84 max PD sets for that tree. So I only showed you say 4 or 5, but there are quite a lot of variations on a similar theme, but that comes from the ability to choose one from each particular component in different ways. And this, so now we could, if we're looking back at the research from before, if we're constructing a study in a similar sense, we might be able to look at our phylogeny we're working with and say, if we're choosing 40% of the species on this phylogeny, how many max PD sets are there of that size? And if there's 400, then we can say, well, how many do we want to sample out of this 400 such that we've got a good spread of max PD sets and we're not weighting them towards certain members of when we could interchange otherwise. And so we can choose a selection method in a sense that would eliminate the bias that could potentially come out of a particular implementation of the greedy algorithm. So 84, for me at least, was a surprisingly large number for such a small tree. And so we've got a question of how big can a number of max PD sets get. So if we consider the family of perfect binary trees, so these are trees which have a number of leaves as a power of 2, and at each vertex we split into 2 subtrees, and these 2 subtrees are a copy of, It always branches into two, all the same height each way there. So, and if we look at particular versions of perfect binary trees, where every length in that tree is the same, then we get this table for different versions, for different number of leaves M. So MTK is my notation for the number of MaxPD sets of size K on tree T, where T is a size N in this case. So it quickly jumps up. So 16, we're in the order of thousands, 32 in the order of millions, and 64 trees are already up at 10 to the 14. So the numbers get quite big, but it's good to note that so for a perfect binary tree with 16 leaves, this number represents about 40% of all sets of 10 species that are possible to choose from. However, by the time we get up to 64, it's about 1/3 of 1% of all the possible sets you could choose out of 42 leaves from that tree. So they get progressively rarer, and that somewhat aligns with this idea that we can enumerate them relatively quickly, but the number of potential sets is growing in terms of n choose k, which grows much quicker. Okay, so I want to, that's in the ultrametric sense, we've got this theorem, and we can use components to work out how many sets of each type there are. And we now want to move to the non-ultrametric case, to have a look at what happens there. And we can get this situation happening in a non-ultrametric tree. You might have a vertex V, which has two child species, X1 and X2. And the length to X1 is much greater than the length to X2. And so we cannot have X2 appearing in a MaxPD set of any size unless X1 is also in that set. Because if we had X2 and not X1, well, we could increase the phylogenetic diversity score of our set we're working with by kicking out X2 and adding in X1. Because then the score would reduce by L2, the shorter length, and we would increase the score by L1. So regardless of whether it's truly a MaxPD set or not, we know that any set that contains X2 and not X1 can always have a PD score increase by adding an X1 in place of X2. And this idea that we would swap out X1 in favor of X2 if given the chance underlies the algorithm to find components in a non-ultrametric tree. And then once we have the components, we can apply the earlier theorem and enumerate MaxPD sets on the tree. So I'm going to give a quick run through of determining components in a contrived example of this non-ultrametric tree. And so we can kind of see the situation I just talked about before with this X1 and X2 appearing in this tree as well, but we've got X5 and X6, which look to be the same distance from their common ancestral parent. And what the process is that we're going to traverse up each pendant edge at the same rate until we hit an interior vertex. So the first step, in blue, I'm covering part of each edge, the same distance up each pendant edge, until we find the X2 2's pendant edge has reached the interior vertex, but we have not reached it from the other side, from x1. And if that situation occurs, that's our way in this algorithm of noting that the earlier situation I talked about has happened, and we're going to remove x2 from our set of feasible vertices in this case. So when we have a non-ultrametric tree, and say we were choosing a MaxPD set of size 4, x2 will never appear in any MaxPD set of size 4. So earlier in the ultrametric case, we could always select any species to appear in any size MaxPD set. But in this case, there's always going to be a size 4 set larger, with a larger PD score than any set which does contain x2. And over on the right-hand side of the diagram here, it turns out that this length was the same for x5 and x6. So they don't get eliminated. However, they are now forming one component. So if we wanted to choose a size 4 MaxPD set here, we would take x1, x3, and x4, and exactly one out of x5 and x6. Continuing on, we go to the next step, and we find that we've eliminated a lot more vertices here. So we've eliminated this whole component of x5 and x6, and we've eliminated x3. And so if we wanted to choose a MaxPD set of size 2, well, unsurprisingly, it's the 2 with the longest edges down here. x1 and x4 would be the unique set, the unique MaxPD set of size 2 on this tree. And we continue further, going up the tree for completeness to the root. And this idea can also be used to calculate components on unrooted trees as well. So we choose the center of the longest path on unrooted tree, and if need be, add a vertex at a distance so that it's in the midpoint of that longest path, and use that as a surrogate root vertex in a sense. And because we're working in from the leaves in towards the middle, that surrogate vertex that we've put in the middle will act just like the root vertex does in this non-ultrametric rooted case. And we can also look at, in the paper in 2005 by Hardy and Goldman, they considered maximizing the phylogenetic diversity score of sets given that we want the set to contain particular species. And if we do that, if we want to achieve that, what we can do is we can take the minimal tree connecting those species to the root and shrink that to a single point, and then run through the same algorithm. And that will tell us which components are containing the leaves we want to add on to make MaxPD sets that do contain a particular set. So I'm going to move on quickly to the next part, which is choosing between MaxPD sets to optimize something else. So we've seen that there can be quite a lot of MaxPD sets given even quite a small tree. And we want to choose among them one that's optimal according to a secondary measure. So this might be their level of endangerment. We won't have all these MaxPD sets, and might want to include as many critically endangered or extinct in the wild species in our set if we're trying to choose a set to add more focused conservation funding to, say. And the way we approach this is we suppose that each species has been assigned a value from a function. And then we want to maximize the sum of these values across a size K MaxPD set. So we're restricting to sets which are MaxPD sets first, and then choosing from among them one that maximizes this score. And there are two algorithms that can solve this approach, and I'll quickly go through these. We have a linear programming approach, and we have a component-wise approach, which relates a bit more to the components we've been talking about. So the linear programming approach, we start by, got this tree, and I've added in IUCN categories of endangerment at the bottom here. So we've got least concern, critically endangered, endangered, and so on. And we've got 6 categories here. So I'm going to replace them with a numerical value from 1 to 6, which represents 6 being most extremely endangered and 1 being least concern. And we would like to create minimum cost flow in the sense that would run through our tree, and branches which have these links added onto the species and connecting them to a sink. But these numbers at the bottom here that our function uses are quite close to, are in the same kind of size range as the numbers that we're using in the tree itself. And so to avoid any complications, what we're going to do is we're going to multiply every edge in our tree by a large number. In this case, by 100 is large enough. And this means that when we run through our flow, that we're really going to prioritize the tree lengths over the function values that we're looking at secondarily. So we really need to, by scaling a tree equally in all cases, this doesn't change any relative heights of any internal vertices, and so it doesn't change any of the components that we care about. And so we're going to always gain the same MaxPD sets as before. And actually, instead of coming up with a flow, there's a slightly a shortcut we can take in this case, which is that after we've scaled the tree up, we can simply add on to the dependent edges these small values of that we're interested in. And this gives us a non-ultrametric tree that we can run through now the greedy algorithm and select a MaxPD set, which has the maximal, takes as many endangered species as possible to the greatest degree. So we'll see that although species X4 is only near threatened, I think it is, only had a score of extinction number of 2. Because it's in every MaxPD set on this tree of size 5, it is contained as well, but the other ones are quite higher up. However, there's a kind of something I brushed over here, which is that determining the scaling factor. I just said, oh, 100 should be enough because I added up all the values along the bottom of the tree, and it was in the order of 10 times something. And so I took another order above that, 100, and used that as the scaling factor. And so for real world data, when edge lengths are whole numbers or rational values, we can do that quite easily. We can scale up the tree so that all the edge lengths are whole integers, or integers, positive integers. And then we can look at the sum total of all of the numbers along the bottom, and then scale the tree again by a number larger than that, and we'll be fine. However, if we have real valued edge lengths, well, the PD scores of non-MaxPD sets may be arbitrarily close to those scores of MaxPD sets. And that means that when we can determine we can find a scaling factor, but that might mean that we have to look and check the PD scores of all n choose k, size k sets of leaves, of which there can be very many, and we want to avoid doing that. So for that reason, for certain particular cases, it's better to use the second algorithm that I'll talk about. And this is an example of a tree where we've got a PD score of 1, x1, 3, 5, and 7 is 63 plus some small number epsilon. And the PD score of x1, 5, 6, and 7, which is not a MaxPD set, is 63. So they're arbitrarily close, but the first set is a MaxPD set and the second is not. So in contrast to this, we can use a component-wise approach. And one bonus is that in this approach, we don't even really need to change the categories to numbers as long as we remember the ranking of these categories and the severity of extinction. So we begin by, we look at the short components. Again, we're wanting to choose a set of size 5. So the short components are these ones again. And if we look at any short component, we know that we're going to choose at most one species from any of these short components. So if we look at the first component on the left here with x1 and x2, we have one critically endangered species and one which is near threatened, which is a lower extinction risk category. And so when we're going to choose one of these species, we're always going to opt for choosing the critically endangered one over the near threatened one. And so on, we look at x5 and x6, we're going to always choose the critically endangered species in place of the least concerned species, and so on. And even at the end here, x9 and x10, we've got an endangered species, which is quite a high level of extinction risk. But we've got a species very closely related to it, which is extinct in the wild. And so that's the highest risk category. And so we would always prioritize that in this case over this, even though it is endangered, because we're trying to create a diverse set as well as one that addresses the levels of endangerment. So we've eliminated some species, and then we look at the tall components. And we want to choose at least one from every tall component. So we go through and we might as well choose the most endangered species in each tall component because we have to choose at least one. So I've circled these in each case here. And then we've got 4 species and we want 5. And so we look among the remaining 3 species that haven't been circled or grayed out. And we're going to choose x3 because it's endangered as opposed to near threatened or vulnerable. And so that's our 5th member that we've added to the set, and we get the same result as the max flow or the other approach. And so those are 2 algorithms which cover ways which we can find MaxPD sets, which also address another measure, or ways to differentiate between MaxPD sets and be a bit more nuanced about it. And that's it for me today. Thank you very much for listening. And any questions, I'm happy to take them.